The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today, I want to talk about, now that we have the machinery for describing vibrations in polyatomic molecules, we go to the quantum mechanics and we start looking at the actual behavior of real polyatomic molecules. And so, we start out with the harmonic oscillator basis set. So we showed classically that we can take a polyatomic molecule and solve the classical mechanics and find the normal modes. We know their frequencies. We know what they are as explicit combinations of internal coordinates. And the important thing is that there are 3n minus 6 normal modes. And that means that the Hamiltonian can be written, or the zero order Hamiltonian can be written as a sum I equals 1 to 3n minus 6 zero order individual oscillator Hamiltonians. And this provides a normal mode basis set. We can say that we have wave function or state vectors v1, v 3n minus 6, which are just the product I equals 1 to 3n minus 6 of vi. So this is wonderful. Once we can describe the normal modes, we can immediately go to quantum mechanics, and we can describe, we can write a complete basis set of normal mode oscillators with which we will represent all complexity that could occur in a real system where it's not harmonic. And so this leads us to the standard model which is the anharmonically coupled harmonic oscillators. So we have harmonic oscillators and we introduce anharmonic coupling terms, and we use what we know about creation and annihilation operators to evaluate all conceivable matrix elements among these zero order states to describe the real problem. And so when we do this, we get what are called polyads. This is an opportunity for unemployed perturbation theorists. I mean, as soon as we do this, we have all sorts of anharmonic terms, and we can do lots of perturbation theory, and many people spend their lives doing that. But one of the things that emerges is there are special cases where, because of near integer ratios of the normal mode frequencies, or combinations of the normal mode frequencies, we get systematic degeneracies. And so the Hamiltonian arranges itself, or we arrange it, but we recognize these near degeneracies. We arrange the groups of near degenerate levels, and we say, okay, now we have to diagonalize blocks of the Hamiltonian because those states are coupled by off-diagonal matrix elements that are large compared to their zero order energy differences. And so we get a lot of insights into vibrational dynamics by looking at polyads. And I'm going to talk about polyads a lot today, and there'll be scaling, matrix element scaling, and selection rules that are amazingly simple and amazingly beautiful. And as a result, one can understand what's called intramolecular vibrational redistribution in a very simple mechanistic way, simply by looking at the structure of these polyads. And another thing that's surprising and wonderful is new classes of motion emerge. So we start out with a picture expressed in terms of normal modes. And remember, the normal modes were explicit combination of internal displacements. And amazingly, local modes emerge. Local eigenstates which are predominantly local. In other words, particular internal displacements. The things that we had to combine to make the normal modes, they reemerge in all their glory. And there are many classes of organized motion that emerge spontaneously from this model that doesn't know about them. We build a model in which we have harmonic oscillators and we have some coupling terms. And the coupling terms are mostly dictated by which modes are near degenerate. And so the molecule sort of selects which are the important, dynamically important anharmonicities. And those dynamically important anharmonicities give birth to qualitatively new classes of organized motion, which appear in characteristic ways in the spectrum that we'll talk a little bit about. And so one example that I expect to talk about is the normal to local mode evolution. And that's why I handed out the relevant pages from the paper, which you already have in toto. So I think I gave everybody a copy of the vector. Okay. So that's what we're going to do. And this is not following the notes that I wrote 12 years ago. And so I'm doing this mostly on the fly. And so let's just see if I can make this clear. Okay, so we start out and we define an effective Hamiltonian, which is a sum of individual oscillator Hamiltonians. And those can be written as remember, omega, because we're spectroscopists, is always in reciprocal centimeter units. And this is supposed to be an energy unit, so we have this factor of hc, which we forget. But to be honest, and since this is a class rather than a whatever, okay. And so we also know that this is going to be multiplied by vi plus a half, but we write v in terms of creation and annihilation operators, or we write this as n sub I, so this is the number operator. And because it's convenient to replace this thing by the number operator whenever it appears, because it makes the algebra simpler, we have two symbols to describe pretty much the same thing. So, and we talked about the creation and annihilation operators earlier. So you know that if I have AI operating on V, we get square root of V minus 1. And so an AI dagger operating on V gives me V plus 1 square root V plus 1 here. And the number that appears here is always the higher of the two quantum numbers. And so it's easily memorable. So we have this way of representing the zero-order Hamiltonian. And so then we say everything else. And this is not the way it's done generally, although keeping with what we did for diatomic molecules, we say there is this zero-order world and everything else that accounts for reality. But for the time being, I'm just going to talk about all of the non-harmonic, beyond harmonic terms as a prime rather than as a series expressed in terms of orders. And okay, so this is then a power series of beyond harmonic. Remember, in the harmonic oscillator, there's no first derivative terms. The only second derivative terms are the squared terms, no cross terms. And so the first time we encounter cross terms is at the cubic stage. And so we have a triple sum for the cubic. And that's Fij, Qi, Qj, Qk. Now, it turns out to be convenient to write these as unrestricted sums, even though it's more natural to think about, you know, the cubed term and the squared plus linear term times linear term as separate, and each of them would have a different factor out here. But combinatorics is much easier, and it's much easier to program using unrestricted sums, and so you really should use unrestricted sums. And then there's the next one, the quartic term, and okay, so that's what we have. And this is the third derivative of the potential with respect to Qi, Qj, Qk, evaluated at equilibrium. And now, in order to be able to make use of creation and annihilation operators and to see the underlying structure of the problem, it's useful to replace the actual normal coordinate displacements by dimensionless objects, and then replace those by the creation and annihilation operators. So there is a simple prescription for replacing an ordinary coordinate with units by a dimensionless quantity, and so we get so this is a factor. This is the normal mode frequency. This is a mass factor, and I haven't had time to figure out what's the appropriate mass factor. And that's something that I'm sorry about, but since I made this up on the fly, and I didn't do this either in the paper, this mass factor does come out of the FG matrix treatment, but I'm not sure what it is. But there is a factor here that has dimensions of mass, and it's knowable. It's just I don't know it. And going from now this dimension quantity to the non-dimension, the dimensionless quantity, and then we write that as AI plus AI dagger, 1 over square root of 2. So that's the procedure. We start out with this thing written out in standard form, and we reduce it to something expressed entirely in terms of creation, annihilation, and number operators. And one reason for doing that is this is quantum mechanics, and we have to be a little careful with commutation rules, and the operator algebra is much more transparent if we go to this. Now, there's more advantages. We also, although in the normal mode Hamiltonian, the momentum has disappeared, it's useful to keep in mind that if we go to a local mode Hamiltonian, there will be off-diagonal matrix elements of the momentum between we already know that if we're writing in classical mechanics, if we're writing things in terms of the internal coordinate displacements, the S's, there are off-diagonal matrix elements between them, or that they're coupled by the kinetic energy term. And so we don't just forget about the kinetic energy or the momentum. The reason we can be lulled into this sense that we can forget about the momentum terms is that in the harmonic oscillator you only have q squared terms. I'm sorry, in the harmonic oscillator you only have diagonal elements. We also have in the harmonic oscillator q squared terms, and we know that they're going to have matrix elements off diagonal in V by plus or minus 2. And we don't just forget them, it just happens they're exactly canceled by the off diagonal by 2 matrix elements of p squared. And as a result, we get to forget about momentum, but it's not gone. It's just that in the standard, the simple expressions, it's suppressed. Now, when we go beyond the harmonic oscillator approximation, the kinetic energy term doesn't change. And so it's gone. Unless we go away from the harmonic oscillator basis set, then it's not gone. And so then we have to be honest about matrix elements of p squared. Okay, so there's a similar operator replacement for p, I might as well just write it, h bar 2 pi c mu, the same unknown mass factor, omega I square root. And now we have the dimensionless momentum, and that is expressed as 1 over square root of 2 times I times A dagger, AI dagger, minus AI. So there's this factor of I, and that's why, in fact, the p squared and q squared terms exactly cancel off diagonal, but diagonally they add. Okay, so we have that. Okay, we're interested in the q I terms that are higher than harmonic. And there are several of these that appear commonly. And it's not just because, well, it is actually because they're the lowest order. We have often a situation where we have cubic terms, and they have the form K122 Q1 squared, Q1 Q2 squared. And because in the scaling, when we replace Q by this dimensionless Q, and there's an omega in the denominator, every power of Q results in a term which is reduced in magnitude by this 1 over square root of omega term. And so the higher the order, the more Q's you have in there, the smaller it's going to be in absolute strength. Okay, so cubic terms are the most important generally beyond the harmonic limit. And they also are a class of term which you often encounter when omega 1 is approximately equal to 2 omega 2. And this is the case for bend-stretch interactions. It doesn't have to be that way, but bends are always lower frequency than stretches. And it's amazing how common 2-to-1 resonances are, and they have a name, Fermi. Fermi resonance is explicitly a cubic term, a 2-to-1 resonance. We could have a cubic term which is a 1-to-1-to-1 resonance. That would not strictly be called Fermi. And, but so this is an important term that you would include in the Hamiltonian. And there are many quartic terms. One of them would be something like this, where omega 1 is approximately equal to omega 2. This is even more common because whenever you have two identical moieties in the molecule, they're going to give rise to local frequencies that are equal. And so you're guaranteed to have degeneracy between local frequencies. And if they're degenerate, then any tiny little thing will mix them. And so it turns out to be really important. And so molecules with two identical stretchers or two identical benders will give rise to this. Now, why is it a 2 to 2 as opposed to a 1 to 1? It's 2 to 2 because when there's symmetry, generally one of the normal modes will be non-totally symmetric, because you're making the symmetric and antisymmetric combinations of the two identical objects. And when that's true, in order to have a term in the Hamiltonian be non-zero, it has to be totally symmetric. All terms in the Hamiltonian have to be totally symmetric. And so if you have a non-totally symmetric coordinate displacement, it has to appear as an even power. And so it is a 1-to-1 resonance, but it appears in the Hamiltonian as a 2 to 2 resonance. And it's extremely common. And even though it's of a higher order than the cubic terms, it's more common and it's more important because the resonances are more perfect. And so these two are the thing. And this one is called Darling-Dennison. I never met Fermi, but I did meet Dennison. He used to go to the spectroscopy conference at Ohio State. And both of these were first most fundamentally understood in the 1940s, about the time I was born. But Dennison was only 20 years or so older than I, no, 30. So he was a very old gentleman when I first met him. So anyway, that's just so we have these kinds of resonances that we want to deal with. Okay. So.
A question about the other cubic terms, like the 1-to-1-to-1 resonance.
Yes.
That you mentioned. That would also happen, I guess, if you have any three identical moieties in the molecule.
Well, but the problem then would be that it's likely that one of them would not be totally symmetric. That when you're combining three things that are identical, you tend to get an A representation and an E representation. And so you would then not be able to have a 1-to-1-to-1. So, but there is a possibility that you have one that's totally symmetric. There are cases when you have a certain coordinate which is not totally symmetric, and another coordinate it's not, but the product of the two makes, so you can have 1-to-1-to-1 where not all three of them are totally symmetric. Two of them have to be not, or all three of them have to be not, and depends on the group. Okay, so for the cubic, we would write the coupling term as 3/6 K122 Q1 Q2 squared. Now, we had the 6 because it was a cubic term, and we have the 3 because we can put, we can have modes 1 and 2 in any of 3 different orders. We can put the unique term first, second, or third, and so that gives us the 6, 3/6. And then, so that's 1/2. And then we can replace these dimensionless Q's by the creation annihilation operators. And so we get an additional factor of 1 over square root of 2 cubed. We have k 1, 2, 2 in reciprocal centimeter units, here and here. And then A1 plus A1 dagger, A2 plus A2 dagger quantity squared. So that's the quantum mechanical operator that appears, that gives rise to off-diagonal elements in the 2-to-1 resonance.
You're absorbing the extra constants into the case?
Yes.
You usually use big K for that, right?
I don't remember what I did, but some of that was idiosyncratic, and so let's make them big Ks. Okay. You see, here I used F instead of, so I get, so this is a big K. And in the paper, it's probably big K, right? Okay. Okay. So we have an off-diagonal coupling term. And now, when you're faced with a real molecule, normally you've done some spectroscopy, or someone else has done some spectroscopy, and so you have a nearly complete set of vibrational frequencies. And so you often look at that thing and you say, oh, well, it looks like I've got a 2-to-1 resonance, or it looks like I've got a 2-to-2 resonance. And so I know that I ought to be careful about writing the Hamiltonian in terms of couplings among states which are near degenerate. And so when you look at the list of the harmonic frequencies, and one of the beautiful things about spectra is that if you're looking in the fundamental region, in other words, only the one quantum in each of the modes, there are very few anharmonic terms that are relevant. And so, and if you do some work, you can get a pretty good estimate of all of the harmonic frequencies. And so you can know that there are or are not likely to be some near resonances. Suppose there are. And suppose you have something that looks like a 2-to-1 resonance. Well, then what you do is you say, I'm going to take those two modes and I'm going to construct, I'm going to organize them according to a new quantum number, what we call a polyad quantum number, which more or less keeps track of the near degeneracies. So we say n is going to be equal to 2 times v1 plus v2 if omega 1 is approximately equal to 2 omega 2. One quantum in v1 is equal to 2 in mode, one quantum in mode 1 is equal to 2 in mode 2. So we multiply the number of quantum in mode 1 by 2. You get 2 points for each quantum in mode 1 and 1 point for each quantum in mode 2. And so we have this, and so we make a little table of the states that we're going to encounter. And so if we have 0 n, then that's the 0, 0 state. If we have 1, that's the 0, 1 state. If we have 2, that's the 1, 0 state, but it's also the 0, 2 state. So here's a case where that fundamental is near degenerate with something else. And so that if you were looking for this fundamental and you saw something that you wanted to assign as this fundamental, it will have some effect being perturbed by this. And often when you have these anharmonic resonances that are near degenerate, you get too many candidates for the 3n minus 6 normal modes, and you know that something is wrong. So it's 1 by 1, 1 by 1, 2 by 2. That's called a dyad. And with 3, we have 1, 1, and 0, 3, another dyad. And then 4, 2, 0, 1, 2, and 0, 4. And if I just I'm picking 10, we could have 5, 0, all the way down to 0, 10, and there's 6 of them. So dyad, triad, sexad. As you go up in polyad quantum number, you get more and more states that are systematically degenerate. And then you say, oh, well, we have cubic couplings, or we have 2-to-1 couplings, and so there ought to be terms in a Hamiltonian that couple this with this and this with that, because we're taking 1 quantum away from here and putting 2 quanta in there. And each of the off-diagonal coupling terms will allow you to take 1 step. You can't go from here to here because that would take 2 quanta away from here and add 4 to that, so you have to do that in 2 steps. So as soon as you think that there is some kind of systematic degeneracy, you make a table like this, and you discover that there is a pattern like that. And if it's a 2-to-1 resonance, then you know you're going to be looking for terms of this form. And but as soon as you express it in terms of creation and annihilation operators, and you say, okay, we have a 2, 0, and we're going to a 1, 2, then by specifying the 2 states that we want to couple, we know exactly which operator we want. We're going to have A1 dagger, A2 squared non-dagger. So you make a list of all of the states that are near degenerate, and then you discover what is going to be the lowest order of term that will couple all of those states. And you know also how to write the matrix elements. So this is going to give a term A dagger 1 to 2 is going to give a square root of 2, and A squared on 2 is going to give 2 times 1 square root. So this is just equal to 2. So once you organize things in terms of near degenerate states, it tells you what terms are going to be important, and it gives you all of the matrix elements among them. You have both selection rule and matrix element scaling. It becomes really trivial, and this is the power of the technique. You don't have to know nothing. And one of the nice things about this also is once you've, say, looked at a dyad, you have determined all of the adjustable parameters that will describe the energy levels. And so, yes, you can go up to 10. The matrix is big. It's a 6 by 6 instead of a 2 by 2. But you know all the elements in that matrix. And so you should be able, based on what you've already determined up to here, you should be able to extrapolate.
Because you've determined the value of K22?
Yeah. Yes. Yeah. And now, of course, nothing is perfect. But usually, the breakdown of an extrapolation tells you you've neglected some other coupling term. And then you know that you have to look for some other coupling term and where it's important from the pattern of the breakdown. And so it's really an amazingly powerful tool. Now, of course, it's totally nonsensical, because the modes, the normal coordinates, or the individual normal modes, are not harmonic. There are diagonal anharmonicities. And so it is a lie, or it is an inaccuracy to represent the problem by putting in on the diagonal, saying the energy is omega times v plus a half plus x times v plus a half squared, and y plus v plus a half cubed, whatever you need. It's a lie because you're only allowed in the harmonic limit to do this. But we put these things on the diagonal. And so they are not harmonic oscillators. They're anharmonic oscillators. And the correct application of perturbation theory is to then calculate matrix elements of the anharmonic oscillators. And that's never done. And we can get away with that for a long time. But that's the reason why this paper was written, trying to say, okay, well, this is a wonderful approximation, but it has to break. Okay, so, but let's just say that we have a way of representing all the energy levels using models based on one or two, a small number of anharmonic coupling terms. And we have this incredible scaling. Then one of the things we can do is we can understand intramolecular vibrational redistribution. Now, when I came into this game, the words IVR, nobody really knew what they stood for because nobody knew what IVR was. It was basically, you know, at high excitation, there's strong coupling between modes, and you get an evolution towards chaos. And so is this redistribution or randomization? Randomization implies chaos. Redistribution implies a mechanism. And this is intramolecular vibration. So IVR was basically one of these non-radiative processes that occur in molecules where people had taken a phenomenological, mostly statistical picture of it, that there was not enough information to describe it. But if we have a polyad model, then we can always write the actual eigenstates as some linear combination of zero-order states. And I'm sorry about this notation. And we can imagine doing some short pulsed excitation where we prepare a system at t equals 0 with a short pulse. And we prepare it not in one eigenstate, but in a state, a zero-order state. Because the zero-order states are the things that often get picked out by excitation by a photon. And we'll talk about that more probably, although how much time do I have? Not a lot. Okay, so in order to describe psi of t, you have to re-express this zero-order state as a sum over eigenstates, doing this transformation backwards. And so we have bij e to the minus ei t over h bar I. So this is an expansion in terms of eigenstates, and this is the time dependence. So it's a superposition of eigenstates, and these two terms come from the unitary transformation that takes you between the zero order and the eigenstate representation, and it's just a matter of which way you're going. Okay, so we know these things because we did diagonalize the matrix, and so if we know by the nature of what the molecule is and what the process is for getting into this energy region, what is the bright state, then we can always say, okay, the time evolving state, we can always write the time evolving state as a superposition. But one of the members of the superposition is going to, I'm sorry, back up. One of the zero order states is usually the bright state. And there are two classes of experiment that prepare highly excited molecules. One is called high overtone pumping, and the other is called stimulated emission pumping. High overtone pumping was very popular in the late 70s because people started to have tunable lasers and started to have sufficient stability with the lasers. They could look at spectra at fairly high sensitivity, and so they were putting all sorts of gases into their apparatus, and they observed vibrational transitions in the visible. And we know vibrational transitions are going to be in the infrared, but they observed, instead of something really complicated, they observed something really simple. They observed a progression of RH stretch vibrations. And it didn't matter how complicated the molecule was, you had a nice, slightly anharmonic progression of transitions, and usually the lasers started around, say, 12,000 wave numbers, which is 4 times 3,000, and RH stretches are 3,000 wave numbers, and so you often had 4, 5, 6, maybe 7, depending if you could go, the lasers were sufficiently blue. So you might see several members of this progression, and it was very well behaved. And there was a lot of interest in IVR on the overtones, and so what one measured was how broad were these things. And the width was somehow related to some IVR rate, and there were a lot of theories what determined these widths. Now, these are not homogeneous widths. They're often, at higher resolution, you start to see some structure under these. They couldn't be homogeneous widths, but in a molecule like benzene, the density of states is so high that it would be impossible to resolve. But in a molecule like formaldehyde or methyl fluoride or something like that, you could resolve the lines, and there was interesting structure. So,
even in the 1970s?
Yeah, even, oh, sure. So there was a lot of stuff and a lot of really stupid stuff said about them. And, but the possibility of looking at high vibrational levels by overtones stimulated an awful lot of belief that you could put a lot of excitation in one bond, because it was clear that these were local excitations. And so it was clear that, you know, you could make benzene with 6 quanta of excitation in an RH stretch, and this width was somehow telling you how long it would stay there. And there were people, in fact, Mike Berry at Allied Chemical built up a big division promising to do bond-specific chemistry based on the appearance of these local modes. I mean, we're chemists. We believe in bonds, and here is something in the spectrum that looks like a bond, a selective excitation of a bond. And so here was this dream that you could excite to a specific, put all the energy into a specific bond and then do chemistry on that bond. And that was sold very hard by Mike Berry and several other people. Okay, it turned out to be impossible. And stimulated emission pumping was invented by me, and this was a different class. This gave access to a different class of highly vibrationally excited state. The local modes were present in the spectrum because the RH stretches were most anharmonic and highest frequency, and so in any given energy region, a state, a zero-order state that has the most quanta in this highest frequency mode, well, that will have the strongest transition. And so because of the anharmonicity and because the fewer quanta, the rule of thumb is each successive harmonic costs you about a factor of 100 in intensity. So if you have some states with 8 quanta in one lower frequency mode, degenerate with states of 6 quanta, you would expect that all things being equal, they're going to be 10,000 times weak. Transitions at those levels will be 10,000 times weaker. And that's true. And so what happened in the overtones is that you had one bright state, one class of bright state, only one. It plucks the system in a way which is relatively special and relatively uncoupled from chaos. Because how, by stretching a bond, it takes a while for the energy to leave that bond. And so it's not a democratic sample of what's going on in the vibrational manifold. And so people were anxious to have some other way of starting out the dynamics, some other class of zero-order bright state. Stimulated emission pumping was, we go from the ground state to an electronically excited state and then back to high vibrational levels of the ground state. And that's driven not by infrared selection rules or vibrational selection rules, but by Frank-Condon factors. And so if you used an electronically excited state with geometry very different from the ground state, then one can get access to high vibrational levels of the ground state that are Frank-Condon selected. And so this profoundly changed the name of the game, because now it's not just one other class of bright state, but depending on which vibrational level of this state you went to, you could get different bright states. And so one could start to pick away at the dynamics and to understand them. And so this led to an explosion of knowledge and experimentation on high vibrational levels, because now we had a much more democratic, or at least a much more systematic view of the couplings that occur at high excitation. Okay, I should stop, but I want to say a couple more things about local modes. So in the early days, one saw experimentally that something appeared in the spectrum that looked like local RH stretch overtones. And then going to these polyad models, we discovered that what are the symptoms of local mode? Well, one of the symptoms is there are almost always two symmetries. I mean, if you take two identical things and combine them symmetrically and antisymmetrically, you have two states of different symmetry. And because the local modes don't know about each other, they become degenerate. And so this degeneracy was the prime evidence for the appearance of local modes. Remember, when you record a spectrum, you don't observe the wave function. But when you fit a spectrum to a model, you have eigenvectors. And you can look at what the eigenvectors are like, and you can write the eigenvectors, express them in terms of the internal coordinate displacements. And by examining the eigenvectors of the effective Hamiltonian, you can see that you do have left oscillator and right oscillator. But the eigenstates are always symmetric and antisymmetric combinations, and that they're degenerate. And if you took psi plus psi minus, where this is just some symmetric and antisymmetric, then you get psi right. And if you take the minus combination, you get psi left. So the first thing is the observation of degeneracy. Then you look at the eigenvectors and you see that they really are localized. But they're not localized in the sense of one state, because you can't do that. You have left oscillator and right oscillator, they're equivalent, but you make the sum and difference terms, and then you take sums and differences of those, you get back to these local mode states. And the other thing is that the intensity pattern. the intensity pattern in the spectrum, the disappearance of all but one class of state, which is recognized as an overtone of something that looks like an RH stretch because it has a frequency on the order of 3,000 wave numbers. And the different RH stretches, OH versus CH, they have slightly different frequencies. And so all of this implied the existence of local modes. And so the thing that I had hoped to get to today, and why I handed out the pages from the paper, was that we can write the Hamiltonian in a normal mode picture or in a local mode picture. And so the Hamiltonian is expressed in terms of frequencies of modes and anharmonicities of modes and coupling terms. So you have two different models. They're really describing the same phenomenon. And you have the energy levels. So you fit the energy levels to frequencies and anharmonicities and coupling terms. So you have a model where you fit the energy levels. And what you fit in the energy levels should be related to the fundamental parameters in these two. So all three of these things are related. And the pages from the paper show how you relate the various quantities. There's a lot of insight into gain from the relationships between these two. The last word is, as is always true in problems in spectroscopy, you have a war between a term that tries to make things simple and a term that tries to make things complicated. And there's usually two representations. And the role of the destroying term and the saving term gets switched in the two representations. And this local and normal picture are a beautifully instructive situation where you see how what destroys the regularity in one model preserves it in the other. And after all, you're trying to, the molecule is trying to go from this to this. So if something is good here, it has to be bad here and vice versa. But this is so universal in spectroscopy that as soon as you get away from textbook spectra, you have a choice of two representations, and the role played by the good and bad terms is reversed. And you never get something for nothing. You never, for example, in Rydberg states, going to case D is a wonderful thing because the rotational Hamiltonian becomes diagonal, but magically the electronic Hamiltonian becomes off diagonal, and most people don't know about that. And so they think, oh, it's just great, let's just do this. So there are many, many cases where you're going to be going between these two representations. There's one that's always better than the other for the particular case, but you have to be careful about remembering what's good and what's bad. It's all relative. Okay, so that's it. I'm not sure what I'm going to do next week, but we're getting close to the end. I think I'm not quite finished with vibrations, but we'll see.